Alright guys, video 3 on gases. Hopefully making a little bit of progress through this. Kinetic molecular theory is basically the theory of all molecules of sorts, but it really focuses on gases and the motion and kinetic energy of those gases. So we just got done talking about temperature, kinetic energy, specifically the fact that it's an average kinetic energy. So let's kind of go through the kinetic molecular theory and see what's going on here. First and foremost, we talk about the fact that particles are always in motion, and this is all states of matter again. So this is your solids, your liquids, and the gases. So remember, our solids are vibrating. Our liquids are technically flowing, even though they do have intermolecular forces holding them together. They're continuously changing those intermolecular forces. And gases have few to very, very little, few to none intermolecular forces, so they have that huge ability to flow. Especially with gases, what that tells us is that there are collisions of the particles with the walls as well as with each other, which is what's causing our pressure, or our measurement of pressure. Okay? With gases in particular is where this comes from, but the particles are very small compared to the distance between them. Why is this assumption important? Okay, well, let's say this is one of my molecules, and this is one of my other molecules, and I'm wanting to measure the volume in which they're taking up. Okay? Well, if these were large enough, so think like maybe they were more beach ball-y, okay, we would have to take into consideration the fact that their volume actually has to be measured to subtract it from the overall volume of the container. Okay, well, that's kind of a pain in the butt. So instead, we make the assumption, and it holds true for pretty much all gases, though obviously there are exceptions, and this is where calculus comes into play, which we will not be touching. We make the assumptions that the molecules are so small that their volume that they take up is nominal compared to the total volume of the container. So therefore, we can assume the volume of each individual particle is 0, and that allows us to assume that the volume of the gas as a whole is just the volume of the container. We don't have to subtract particle size or anything weird. Again, it keeps calculus out of the math, which is what we want right now. Okay? Particles exert no force on each other. Okay, what that means is as they're bouncing around and slamming into each other, they're not going to attract or repel each other, which means no IMS. Now, this in technicalities is not a true statement, but it is used to explain the math of gases and to keep that math simple. Again, if you start coming into considering the fact that as two molecules slam into each other, they may very well attract to each other and therefore slow down, or you have two molecules slamming into each other and they repel each other, therefore speeding up away from each other, you now have to take that in consideration and have to, again, go into the calculus for the math. We don't want to do that. So really what this theory does is it simplifies our math for us. It also gives us an idea of what an ideal gas is, which again is a simplification of the math. Okay? Average kinetic energy is proportional to the temperature. So again, remember, temperature is a measurement of average kinetic energy. And of course, temperature is measured in Kelvin. So that's what the kinetic molecular theory is. Really what this does is it allows us to not have to worry about calculus and to really think through gases in an overarching theme, which is our ideal gas. Okay, so what is an ideal gas? An ideal gas is something that fits into all of these assumptions that the kinetic molecular theory makes perfectly. So again, particles are very spread apart, and they're very small compared to the size of the container. The collisions between the gases are considered elastic collisions, which if you're in physics, hopefully we've heard that term as well, which basically means as they collide, they bounce off each other with the same amount of energy they had to begin with, meaning no attraction, no repulsion. No kinetic energy is lost, again, through those elastic collisions. There's no force of attraction between them, again, going back to that elastic collision, so no IMFs is really what that's referring to. They are constantly in motion, okay, and moving rapidly, therefore they contain kinetic energy. And of course, the average kinetic energy is, again, dependent on the temperature, so temperature is a measurement of kinetic energy. It has nothing to do with the identity of the particles. So remember, speed or velocity has to do with the identity of the particles, but the actual average kinetic energy portion does not. I can have two gases at the same temperature, therefore they have the exact same kinetic energy. They may not have the same mass, therefore they're not moving at the same speed, but they have the same kinetic energy due to the force of collision and everything else that's going on. So that's really why we have the kinetic molecular theory, is so that, sorry, I don't know what I just did, so we can define an ideal gas. Now, are gases actually ideal? No. As a matter of fact, there's no such thing as an ideal gas. Why do we talk about ideal gases then? Because we want to keep our math simple and not deal with silly little calculus things. But just because we don't want to deal with calculus doesn't mean we can't understand the difference between an ideal and a real gas. So here are just some of the big differences in being able to identify those differences. So first and foremost, tiny particles that are very spread out relative to their size. This is only going to be true at high temperatures and at low pressures. Why? Because at high temperatures, okay, we're going to have a lot of kinetic energy. So we're going to have a lot of motion, very spread out, moving very quickly. Also at low pressures, think about what low pressures mean. Low pressures mean that there's not a lot of collisions. Well, why would there not be a lot of collisions? Well, either because there is a small amount of gas particles, or there's a large volume, which allows the gas molecules to spread out really, really far. So what happens at low temperatures and high pressures? Okay, well, at low temperatures, what I want you to think about first off, this is going to decrease our motion, which means the molecules are going to have a tendency to be much closer together. Okay, well, if they're close together, they're going to be interacting with each other a lot more, and there's going to be more area that the molecules themselves are taking up versus being really spread out and separated. At high pressure, same idea. What does high pressure mean? It means there's either a lot of the gas, or it means there's a very small pressure, or a small volume, excuse me. Which means, again, close together and having to interact with each other. Okay? And the idea of having an elastic collision, well, that doesn't actually exist, because the minute, think about Coulomb's law, the minute two things come in contact with each other, one of two things is going to happen. They're either going to repel or they're going to attract, period, in the story, because even our nonpolar things, remember, have LDFs that we have to take into consideration. So a real gas has IMFs, and therefore collisions will never actually occur elastically. They will always be inelastic collisions, meaning repulsion is going to cause kinetic energy to increase, whereas attraction is going to cause kinetic energy to decrease. Okay? And then no force of attraction, again, is what we just talked about with IMFs. Oops, sorry guys, don't know what just happened. There we go. Force of attraction is the IMFs here. Okay, so let's see what we need to be able to do with this. All right, well, here's two problems. What I want you to do, pause your video and see if you can answer them and see what you come up with. Okay, so hopefully we've had a chance to actually pause, think through these, and are actually doing this and not just letting the video run along. I'm actually wanting you to try the problems, go figure. Okay, so let's check out this first one. Under which of the following conditions of temperature and pressure would a 1 mole of a real gas, carbon dioxide, behave most like an ideal gas? So again, what makes an ideal gas? No IMFs and spread out. And those really are the two main factors that make an ideal gas. So now we have to take into consideration temperature and pressure and figure out which one of these combinations is going to allow the gas to be very, very spread out and therefore have no IMF interaction, or very few IMFs, because again, think Coulomb's law. Yes, I'm going to keep coming back to Coulomb's law just to drive you absolutely and utterly batty, and because it's important. That very spread out is going to cause our radius to be huge, or very, very large, which causes our force to be very small between them. So again, little to no IMF interaction. So what are we looking for here? Okay, we are looking for a high temperature. Remember, in a low temperature, that means a decrease in kinetic energy, which therefore means a decrease in velocity. So not spread out, actually much closer together. This is where things are going to start condensing possibly. So we're looking at one of these three high temperatures, which gives us a high kinetic energy. and therefore a high velocity. The next thing we're looking for is a pressure that will be conducive to being spread out. So really what we're looking for is a low pressure, which again will be indicative of either a small amount of gas or a lot of volume for the gas to be able to move in. So this high kinetic energy is only really worthwhile if the gas has a lot of movement to be able to run around. So think about the idea of a bunch of kindergartens that just got given cupcakes. Do you want them in a tiny little classroom where they're going to be bouncing around driving everybody crazy? Or do you want to be able to throw them out on a football field and let them run? Okay, so high kinetic energy is really only beneficial if you have a lot of space, again indicative by low pressure, for the gas to be able to move through. So 100 ATMs, very, very high. So we can rule those two out automatically, which we've already ruled out A technically. So now we look at point 1 and 1. Well, which one's more ideal? The lowest one. So in technicalities, B is going to be our best answer here. Okay, next one. Which of the following gases would be the least ideal? Well, what makes a gas least ideal? Really, it comes down to, with no pressure or temperature to look for here, IMFs. So what you're looking for here is something with the strongest IMFs. Well, if we go through and draw our Lewis dot structure for all of these guys, notice what we're going to get. We get all nonpolar substances, therefore we're dealing with strictly LDFs. Well, what makes one LDF stronger than the other? Remember, it comes down to the amount of electrons and that uneven distribution of electrons. So if we're looking at this, oxygen is going to have a total of 16 electrons, hydrogen is going to have 2, bromine is going to have 70, and chlorine is going to have 34. Well, which one has the highest amount of electrons? Bromine, therefore it has the highest LDFs, strongest intermolecular forces, making it the least ideal. Okay, from here, let's talk about our gas laws very, very quickly. We've got Boyle's, Charles, Gay-Lussac's, and as well as our combined gas law. So remember, when we're dealing with these three gas laws, we're talking about the same sample of gas. So we're taking something that's at a specific pressure and volume, changing the pressure and volume, and seeing what happens. And so remember with this guy, as we increase our volume, we are decreasing our pressure, so we have an inverse relationship between pressure and volume. As we increase pressure, notice we are decreasing volume. And again, that should make a little bit of sense. So remember, pressure is the amount of collision. So if I'm dealing with the same sample of gas, I condense it down into a smaller volume, it's going to be banging around a lot more, therefore causing more pressure. We then have Charles, which is our volume and temperature. This is a direct relationship. As I increase temperature, I am increasing my volume. And again, the reason being is because pressure is being held constant here for the same sample of gas. So again, that should make a little bit of sense of what's going on. We have Gay-Lussac's, which is pressure and temperature. Again, direct relationship. If I increase my temperature, I'm increasing my pressure, assuming that volume is being held constant in this case. And again, this should make sense. If I'm increasing temperature, I'm increasing kinetic energy, therefore I'm increasing the amount of collisions, therefore pressure. Okay, and we have the combined gas law, which takes the three gas laws and combines them together. So not as clean, being able to come up with a relationship. Okay, but we have the same idea where we take one of these and change it, and we can calculate the other ones. The big thing here is to remember that temperature for all of these will always be in Kelvin. You cannot do these calculations in Celsius. It will not work. Okay, and again, that is because we've standardized these equations in Kelvin so that we don't end up with an accidental negative pressure or volume. Okay, and then of course that does lead to our ideal gas law, PV equals nRT, which we should be fairly comfortable with, P being pressure, commonly in ATMs, volume in liters, commonly, N is moles, and the reason I'm saying commonly is because of our R value. There are different R values, which you can see on your formula sheet. I believe you have one with ATMs, so a different pressure, okay? So that is where we do get some differences, and of course temperature is always in Kelvin. So what we're going to do, we'll come back and talk about Avogadro's law in a little bit. We're going to pause here for today, and you're going to work on some problems just to make sure we're comfortable using these gas laws. Again, if you have questions, let me know. Thanks, guys.